This is lesson 2.3, inverse of a matrix. And that's what we're going to spend our entire lesson on is just looking at this idea of an inverse, looking at some of the mathematical properties that relate to the inverse of a matrix, and so on. So before we get into the matrices, I want to take us back to algebra and the real number system and just kind of remind ourselves that when I take, or if I have an equation ax equals b, where a and b are simply real numbers, and I want to solve for a, typically we might think in our minds that we're going to divide by a, which would be accurate. But another way to think about that is when we divide by a, we're really multiplying by the inverse of a. If I take a inverse times a times x, I also then have to do that on the right side with b. But that a inverse, that's just going to be 1. And so my answer to solving for x is the inverse of a times b. Okay. In other words, think of this as the multiplicative inverse of a. So we're going to call this the multiplicative inverse of a. Every real number has an inverse except for 0, because you can't take anything divided by 0. But every real number has an inverse, and so this would hold true for anything except for 0. Similarly, we can apply the same idea to matrices. So if, for example, well, let's get into the definition first, and we'll do the example. But so by definition, we talked a little bit about this, or got a little bit into some of these ideas before in the last lesson. But an n by n matrix, a square matrix, is what we call invertible or non-singular when there exists another n by n matrix B such that a times b equals b times a equals the identity matrix. Okay, so in other words, I've got two matrices that are square, and if I multiply them in either order, I will get the identity matrix. Okay, and we saw this idea when we talked about the identity matrix, like I said in the last lesson. We're going to just build on this now in this lesson. So b would be the inverse of a, which we denote b to the negative 1, or b inverse. Or you could say that a is the inverse of b. They are inverses of each other. Okay. So how does this work then? Well, let's say I want to find the inverse of a matrix then. So so great, this is all true, that we've got a matrix and its inverse. How do we find the inverse? Well, very simply, we're going to keep in mind this idea that a matrix times its inverse gives us the identity. Okay? So in this case, if I was to take 1, -2, 2, -3, if I take matrix A, and I multiplied it by some other 2 by 2 matrix, that would give me the identity matrix 1, 0, 0, 1, then this has to be the inverse matrix, right? If this is A, this is the identity, then in order for this equation to work, to get the identity as an answer, a solution on the right side, this missing matrix has to be the inverse matrix. Right now, we have no idea what that matrix is. So what I'm going to do is I'm just going to call this A, B, C, D for its entries. Now, we have an equation, and we can solve this equation, because if I multiply these out, if I multiply the two matrices on the left side, I will get, for example, A minus 2C equals the first entry in the right side matrix, equals that 1. And likewise, if I take the first row and the second column, 1 times B, and -2 times D, that equals 0. And now if I go down to the second row, 2 and -3 times AC is 2A minus 3C is equal to 0. And 2B minus 3D equals 1. If you look at those equations, and I've intentionally written them the way that I have so you can hopefully see this very clearly, you have two systems of linear equations. You have one with A and C, you've got another with B and D, and we can solve those systems individually. Now, again, I'm not going to go through all the work of showing this, but if we were to solve these systems, whether it's using augmented matrices or just simply using like an elimination substitution method, we would find that for the first set, A is -3 and B is -2. And for the second set, B is 2 and D is +1. Okay. What that tells me then is that my inverse matrix is -3, 2, -2, 1. So the check for that, if I want to actually check to make sure that this is correct, is simply to take A times A inverse. If I take matrix A, I multiply by the answer that I just found, the inverse -3, 2, -2, 1. When I multiply these together, -3 and +4 is 1. +2, -2 is 0. -6, +6 is 0. 4 minus 3 is 1. And sure enough, I get the identity matrix when I multiply those two together, telling me that that is the inverse of A. All right, so let's look at another way to solve this. So we're just going to do the same problem. And again, not that you would have to do this, but just to kind of think about this a little bit differently. Because I know that basically what I'm doing is I'm taking this matrix A, and I'm in essence trying to create an inverse matrix. I'm trying to create this 1, 0, 0, 1. And in doing so, I find the inverse of A in that process. So what I'm going to do is I'm going to set up an augmented matrix where I'm going to take matrix A and the identity matrix, and we're going to apply the Gauss-Jordan elimination method to simplify this down. So this is A. Basically, this part of it is A. This part of it is the identity matrix. And if I apply Gauss-Jordan, and again, I'm not going to go through this, but if I apply Gauss-Jordan elimination, what I end up with is a matrix where the first part now is the identity, right? Because again, when we apply Gauss-Jordan elimination, we are trying to create that that identity matrix where we just have that diagonal of ones, everything else is 0. And this is -3, 2, -2, 1, which is the inverse matrix. So it's another way to think about solving this. That again, it doesn't matter. You can algebraically set up your systems like we did in the first way, and then solve those systems to get your values, or you can apply Gauss-Jordan, just making an augmented matrix where you've got A and I, and then you just work it through until you get that 1, 0, 0, 1 on the left side, so that this now is I, and this is your inverse matrix. All right, and this will work, all of this that we're doing will work for any square matrix where the identity is also of the same size, obviously. Okay. Now, if for some reason you couldn't reduce it down, in other words, as you're going through this Gauss-Jordan elimination, or even if you're doing it algebraically like we did above, if you cannot get an answer, it simply means that the inverse doesn't actually exist. So it's possible to get a matrix where you can't solve it, where the inverse just doesn't exist. And you would know that really kind of just through that process of solving it, either algebraically or with a matrix. But let's look at another situation here. So if you look at the answer here and look at the original. So if I look at the 1, -2, 2, -3. So I'm gonna, in fact, let me just kind of pull this out here. So this is our answer, right? And our A and our answer. Let me just kind of clean this up a little bit so we can see this better. So this is A, this is its inverse. Notice the similarities in the values of those two matrices. Now this is specific for a 2x2. You won't quite see this in 3x3, 4x4, though you do sometimes. But notice that if I look at the diagonals in particular, if I look at that diagonal and I look at that diagonal, and then I look at that diagonal and look at that diagonal, you should notice something there. If we did more of these, you'd really start to see the pattern come out. Basically what happens is in a 2x2 matrix, these two numbers are simply going to switch places, and these two numbers are going to take opposite values. Now, there's one other piece to that we need to talk about, because that's not all it does. There is actually more to it. It just happens that in this case, we simply flip those numbers, but there are other cases where it's not quite so simple. But in this case, what's going to happen is that I'm going to think of this as being in the form A, B, C, D. Okay, so we're going to just assign the first entry, the top row A, B, the bottom row C, D, just so we can kind of talk about algebraically what's happening here. So the first thing that we're going to do is we're going to find AC minus BD. So I'm going to take A times, whoops, not AC, AD, apologize for that, AD times BC. AD, so we're multiplying that diagonal, 1 times -3, and then subtracting the other diagonal, -2 times 2, or 2 times -2. In this case, I get -3 plus 4 is a +1. And I'm going to just call this E for now. Now, if I do this and this is 0, that means that there is no matrix, or excuse me, no inverse matrix. Okay, so in a 2x2, and again, this only works for a 2x2, if you find that what's called the determinant of the matrix, that AD minus BC, if it's 0, there is no inverse matrix. If it's not 0, then we're going to proceed and go ahead and find the inverse. Now, the way that we find the inverse is whatever that value is that we just found, this determinant, I'm going to call E, we take 1 over E and we multiply it by the original matrix, but flipping D and A, and then making B and C the opposite value. So we're going to flip the position of D and A. We're going to just flip the values from positive to negative, negative to positive for B and C. So in our example, because E is 1, we're just going to have 1 over 1. So we will just have -3, 1, those flip, and then -2 becomes +2. The +2 becomes a -2. And if you'll notice that -3, 2, -2, 1 is the inverse matrix that we found above. Now, obviously, if that determinant, if this value is something other than 1, it will change the actual values in your inverse matrix. Okay, so if this was, for example, 2, if the E value was 2, we'd be multiplying by 1/2 all of the values in our inverse matrix, would actually be half as much. So it just happened that in this case, when we look at this relationship that I talked about earlier, it just happens that all we had to do were flip some numbers and change some signs because that determinant was 1. But if that determinant is other than 1, then you won't see that pattern quite as clearly necessarily. All right. So that's, again, only for 2x2 matrices, but it's a faster way of finding the inverse. You simply you multiply the diagonals and subtract them, and then you take that determinant and you just write it as 1 over that number times the kind of reformatted matrix. All right, let's move on and let's talk about a couple of theorems here. So if A is an invertible matrix, K is a positive integer, C is a non-zero scalar, basically what this is saying is that, again, like we talked about in the last lesson, a lot of things that happen with the real number system also apply to matrices. So the idea that if I take the inverse of an inverse, I'm going to get my original back. If I take a matrix to a power and then take the inverse, I can flip it around. I can take the inverse first and then to a power. Just like I could say that, for example, a squared, if I'm looking at the real number system, if I take a squared cubed, that's the same as a cubed squared, right? It doesn't matter which order I do those exponents in. C, or number 2, oops, that should be number 3. Sorry about that. If I have C8 and then take the inverse of that, so if I multiply by a scalar and then take the inverse, I can in essence distribute the idea of the inverse. I can just do 1 over C times the inverse of A. And then 4 is really a lot like 2. Whether I take the transpose first and then find its inverse, or find its inverse and then take the transpose, I'm going to get the same result both times. And then we've got another theorem that, again, notice this is a little bit different though. Here, it's saying that if I multiply two matrices together, A and B, and then find the inverse, it's not the inverse of A times the inverse of B. We actually have to flip the order here. It's going to be the inverse of B times the inverse of A. So just watch that order carefully with that particular theorem, okay? So what I want to do is just run through some examples that, again, just kind of highlight, in particular, this second theorem. And we're going to solve this in both ways. So in other words, we've got these two matrices in our example, A and B. And what I want to do is I want to look at in the theorem, both the left hand and the right hand, and use both sides to solve AB to the negative first, or the inverse of A times B. In other words, we're going to first solve this by multiplying A and B together and then take its inverse. And then I want to do the same thing, but I want to take the inverse of A and B first and then multiply them together, just to illustrate that, again, we should, if we do this correctly, we should get the same results. All right. So for the first one, we're going to multiply A and B together, which is just, in this case, -1, -2 is -3. 4 and -6 is -2. -2, -3 is -5. And 8 minus 9 is -1. So that is our A times B. And now we want to find the, really sloppy on this one today, sorry. We're going to find the inverse now of that. So to find the inverse, I'm going to apply that rule we looked at before. So I'm going to find AD minus, or AC minus BD. So I'm going to take -3 times -1 minus a -5 times a -2. And that is going to give me a determinant of -7. All right, so to find the inverse now of AB, I'm going to take a -1/7. Remember, just do 1 over that number that we just found. And then I'm going to flip the -1 and the -3. And then the -2, -5 just become positive. And so my final answer here is going to be a +1 over 7, -2 over 7, a -5 over 7, and a +3 over 7. So that is the inverse of A times B, where we multiply A and B first, and then we take the inverse. Now let's go ahead and do the same thing, but this time we're going to find the inverse of each of the matrices separately first, and then multiply them together. So let's start by finding the inverses. We'll just start with B. So again, if I take the diagonals and subtract, we get -7. So -1 over 7 times 3, -1, -4, -1. So that matrix is -3/7, +4/7, +1/7, and +1/7. And then A inverse. Well, in this case, if I multiply and subtract the diagonals, I have a -3 plus 4 is a +1. So actually, in this case, we're just going to have to do the switching around. So -3, 1, and then +2, -2. Okay, so now if we multiply those together, I'm going to take B times A. And let me rewrite this a little bit bigger here. So this is going to be B inverse times A inverse. So -3/7, 4/7, 1/7, 1/7. And then times A inverse, which is -3, 2, -2, 1. So we've got basically, I'm going to just kind of ignore the sevens because we know all of our denominators will be over 7 in our answer. So I've got a positive 9 minus 8 is a positive 1 over 7. Second column is going to be negative 6, and 4 is a negative 2 over 7. And then second row, we're going to have a negative 3 and a negative 2 is a negative 5 over 7. And then a positive 2 and a positive 1 is a positive 3 over 7. And you'll notice that, in fact, again, our two answers are the same. So just kind of, at least in the case of one example, just kind of showing through that example the theorem that we looked at earlier. All right. So that is actually it for this lesson. Again, just kind of be aware of those theorems, be aware of some of the properties that that hold for matrices in a lot of the same ways that they hold for real numbers. And I'll see you in the next lesson.